To help students build a strong and flexible understanding of equivalent fractions requires the use of context and models in which the goal is to rename a fraction amount. As you notice in the figure below, area models are a good place to begin with understanding equivalency. Ask students to consider what equivalencies are possible and have them justify their thinking beyond what they could build with their manipulatives. A question you could ask: what equivalent fractions could you find for 3/4 if you've had 16ths in your fraction? Well, there's four groups that fit into 16, so you would have 4 separate groups of 3, 4 separate groups of 4, which makes 12/16. Activity 14.18, apples and bananas. Use apples and bananas activity, or just have students set out a specific number of counters in 2 colors, for example 24, with 16 of them red and 8 of them yellow. When 24 counters make up the whole, ask students to group the apples and bananas into equal sized groups, such that a group has to have only apples or only bananas. Change them to find as many ways as they can. For each that they find, record the fraction name as apples and bananas. They can record each option that they find in a table, which helps notice patterns. Ask questions such as, is it possible to have fruit in groups of 4? To encourage students to think of different ways to form equal-sized groups, counters can be arranged in different groups or in arrays. In the figure below are some examples. So you have the count of 16 and the total of 24 apples being counted, the 24 total, and you have 8 as the count and 24 as the total. Make 16 apples into groups of 4. You can make 8 groups of bananas into groups of 4. When thinking of 8, you can have 16 grouped into 8s and 1, so it's 2/3 of the apples are of the 24 apples, and 1/3 of the bananas, because there's only 8 of them, are of the 24 bananas. Area models are a good visual for connecting the concepts of equivalency to the standard algorithm for finding equivalent fractions. Multiply both the top and the bottom number by the same number to get an equivalent fraction. Ask students to look at the pattern in the way that the fraction parts in both parts and the whole are counted. By creating equivalent forms of 6/8, you might multiply to get 12/6 or divide to get 3/4. To write a fraction in simplest terms means to write it so that the numerator and the denominator have no common whole factors. 2 things to think about. Notice that we didn't use the phrase reducing fractions, because that would imply that the fraction is being made smaller. This terminology should be avoided. Fractions are simplified, not reduced. Do not tell students that fractions answers are incorrect if they are not in simplest or lowest terms. 1/6 plus 1/2 equals 2/3 or 4/6 are correct. 4 different ways to compare. Same size denominators. To compare 3/8 and 5/8, think about having 3 parts of something and 5 parts of something. The denominators are the same, the 5 is greater than 3. Same numerator. Consider the case of 3/4 and 3/7. If the whole is partitioned into 7ths, the parts will certainly be smaller than partitioned into 4ths. More than or less than benchmark. The fraction pairs 3/7 versus 5/8 and 5/4 versus 7/8 do not lead themselves to either of the previous thought processes. In the first pair, 3/7 is less than a half. 5/8 is more than a half. Therefore, 5/8 is the largest fraction. In the second pair, one fraction is greater than 1, the other is less than 1. The one that's greater than 1 wins. Closest to benchmark. Why is 9/10 greater than 3/4? Each is one fractional part away from a whole. 1/9 is only 1/10 away from a whole, and 3/4 is a fourth away from being a whole. So 5/8. No, and similarly, notice that 5/8 is smaller than 4/6 because it is 1/8 more than a half, while 4/6 is 1/6 more than a half. Hopefully you have recognized that one reason fractions are not well understood is that there is a lot to know about them, from part-whole relationship to division construction and understanding representations across area, length, and set models. Give a greater emphasis to number sense and the meaning of fractions rather than root procedures for manipulating them. Provide a variety of models and contexts to represent the fractions. Emphasize that fractions are numbers and making extensive use of number lines as representing fractions. Spend whatever time is needed for students to understand equivalency, including flexibly naming of a fraction. Link fractions to key benchmarks and encouraging estimation. Common challenges and misconceptions of these fractions. In the first one, find fraction values that are on a number line. Number 2, you could have students create their own representation of fractions. Fractional parts must be the same shape. Provide examples and non-examples of partition shapes. Fractions with larger denominators are bigger. Use context. For example, ask students whether they would rather go outside for half an hour or a fourth of an hour or a tenth of an hour. Fractions with larger denominators are smaller. Teach estimation and benchmark strategies for comparing fractions. Representing fractions greater than 1. Infuse fractions of various magnitudes less than, equal to, or greater than 1. Determining a whole when given a part. Encourage students to draw a number line and use another tool.